Changing magnetic field. We have a circular coil, and that's this guy here. It lies on a horizontal tabletop. A downward magnetic field crosses the tabletop, and the field magnitude increases from 0 to a maximum value of 4 Tesla in 0.5 seconds. What is the maximum magnetic flux through the coil? What is the magnitude of the induced EMF in the coil? Then the coil has a net resistance of 0.6 ohms. What is the magnitude of the induced current in the coil? What is the direction of the induced current? And that'll be a Lenz's law issue. What is the rate of thermal energy produced? Because the magnetic field is perpendicular to the cross-sectional area of the loop, we get the maximum value just by multiplying the magnetic field by the cross-sectional area and the amount of loops we have. So we have N times B. Cross-sectional area is pi r squared, right? That's a circle's area. 10 loops. Here's the magnetic field. Here's our area. And what happened here? Why is that 0.3 meters? It's 30 centimeters. And to convert to meters, move the decimal 2 to the left, and you get 0.3 meters. And we get 11.3 Webers. What is the magnitude of the induced EMF in the coil? So here we have Faraday's law of induction, and this negative sign here, that tells you that the induced EMF will create a current that will create a magnetic field that opposes the change in the external magnetic field applied to the loop. And that's Lenz's law. Yep, just that negative sign. So our initial flux is 0, and typically whenever we have a change, it's final minus initial. The final flux is 11.3 Webers. We calculated that on the previous slide, and it takes half a second to do that. And the negative sign here, really, that's just giving us the direction. We don't need it because we're asking for magnitude, and we get 22.6 volts. There's a net resistance in the coil of 0.6 ohms. What's the current? Ohm's law. Okay, V equals IR, or I is equal to V over R. Now we calculated EMF, but that's interchangeable in this case for voltage. So we put the 22.6 volts over 0.6 ohms, and we get a current to 37.7 amps. Seems pretty unrealistic for this problem, but the numbers check out here. That's a lot of current. And 4 Tesla is a lot of magnetic field too. What is the direction of the induced current in the coil? Lenz's law says a current will be generated that will create a magnetic field to oppose the change in magnetic flux from this external field. So if we look at this three-dimensionally here, we've got this field increasing, going down through the table. So we need a field to come up through the table to counteract that. So you use the right-hand grip rule, and if you stick your thumb over here, and here's the rest of your fingers, and grab the wire, obviously just on paper, you wouldn't grab a wire of 37 amps. If you go in that direction, it tells you that that current will generate a magnetic field coming out of the page, which is what we want. That will counteract the change in flux. Right? The flux is increasing down. We want to counteract that by having a magnetic field up. So if I have the thumb pointing here, it's going like that. And what is that? That's the counterclockwise direction. What is the rate of thermal energy produced? Well, the rate, whenever you see rate of thermal energy, that's energy per time, or E over T. And what's that? That's power. Power is energy over time. Now in a circuit, power equals IV, I squared R, or V squared over R. We'll go ahead and use IV. We multiply the current, very large current, times voltage, not too bad a voltage, and we get 852 watts. So that's a lot of power there. That's like 12 light bulbs.